Okay, so here we are for part 3 of the titrations lecture video. Again, I'm going to follow this up with some Workout Wednesday style problems that are going to be added to the D2L over the coming days. So the last situation that we have not looked at yet is taking a weak base, and in this case we're going to use methylamine, which is on our reference material. We're going to use the values from our reference material, and a weak base titrated with a strong acid. So our titrant in this case is going to be a strong acid. We're going to work with the exact same values for concentration and for volumes, just to keep it simple, but realize that these values do not have to be the same, right? They do not have to be the same. In the situations you're going to see in Workout Wednesday or on your assessments, they won't be, okay? So here we are now dealing with the creation of a conjugate, right? So if we remember, right, we are dealing with a conjugate acid. Now nitrate is a conjugate base, however it is neutral, and here we have an acid and a base. If we look at these values at step 1, right, which is halfway to the equivalence point, right, halfway to the equivalence point, we're dealing with a before concentration that is, a before number of moles that is 0.01. We are dealing with 0.005. We do not have any, and again, we're not so worried about a neutral ion in solution, right? Now, our limiting reagent is 0.005, 0.005. We have used up all of our acid. We are left with 0.005 moles of methylamine and 0.005 moles of the conjugate. Again, if we get into a systematic habit of doing these steps each time, there should be no issue. These numbers may change, but the process will not change, right? Right here you see that you are before equivalence because you have not used up all of your analyte in this case. So since you have not used up all of your analyte, we can utilize Henderson-Hasselbalch. So pH is equal to pKa plus log of A minus over HA. Now, is this useful right now when we're dealing with a base that we have the pKb for? You could use this, but I would suggest to utilize POH is equal to pKb plus log of the conjugate acid over the base. And again, this is on your reference materials. On your reference material. So remember that. Always use your reference material. So I suggest you use the POH. Now, you're going to have to convert that to pH, but that's simple. Now that you know the number of moles, you should also realize that the concentration now is going to, of each of these, is going to be 0.005 moles all over. The total number of volume is 0.15 liters, so that concentration is going to be 0.033. So that's going to be the concentration for both of these. Therefore, again, remember POH is equal to pKb plus log of 1, because all I'm doing is showing that these two divided by each other equals 1, and therefore at the halfway point, POH equals pKb. Again, you're not always going to get the halfway point. I'm just doing this for simplicity purposes. Sometimes this may be less than 1, sometimes this may be greater than 1, right? Does not mean that we are at equivalence yet. So here, we're still before equivalence, and since POH is equal to pKb, negative log of the reference, go to your reference material, I think it's 4.4 times 10 to the negative 4. And now we have a POH that is equal to negative log 4.4 e to the negative 4. 3.36. So POH 3.36. You can't go to this chart yet because this chart is pH. So pH is equal to 10.64. So let's go to our chart and I'll do this in a different color. So a little higher than 10, 8, 9, 10.64 at 50 is roughly about there. Okay, so we are before equivalence. We are in the buffering region, right? So we can use Henderson-Hasselbalch. We can use Henderson-Hasselbalch. Stoichiometry, Henderson-Hasselbalch. You could use ice table if you wanted to, but again, we dropped X. Why? Because the KB is much smaller than the concentration that we're working in. Okay. All right. Now, let's talk about different scenario. Okay. Now we're talking about at equivalence. So at equivalence, we're dealing with 100 milliliters of both. That means, as far as the moles are concerned, we're dealing with 0.01 moles, 0.01 moles. We don't have any plus 0.01 moles, 0.01 moles at the end. 0.01 is what we're using up, and we have none of our reactants, none of our analyte or titrant. We have reached equivalence where the number of moles are equal. Now we are left with the conjugate acid of our base that we've been working with. So this is another place where we need to look at KB, 4.4 times 10 to the negative 4, and we need to solve for the Ka, because now we are in acid land. Why? Because now in solution, CH3NH3 plus is going to interact with water and create and establish an equilibrium that creates hydronium plus now what will be the conjugate base of our acidic scenario. That interaction, that thinking and process to get right here at equivalence is where a lot of people are going to make mistakes. Okay, so now that we know this, now again at equivalence we need the ice table. To get the ice table and to use it we need Ka, Kw, but we also need the concentration of our methylamine conjugate, which is equal to 0.01 moles divided by 0.2 liters, which is equal to 0.05. Mole. Okay? 0.05 molar. So, 0.05, we're never worried about water. 0, 0, plus X, 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 minus X, 0.05 minus X. This interaction, again, is acidic, therefore we need the Ka, therefore 1e to the negative 14 divided by 4.4 e to the negative 4 gives us a Ka equal to 2.27 times 10 to the negative 11, right? Very small, so we don't expect this to be very acidic at all, right? Just based off of the Ka value, we don't expect that. Now, we can set up Ka equal to x squared over 0.05 minus x. But remember, we can drop x because of our Ka being so small, so we can solve for x, and x is equal to H3O plus, which is equal to the concentration, so times 0.05, square root, second answer, we're dealing with 1.1 times 10 to the negative 6 molar, so 1.1 micromolar. And now we have a value that we can plug in to solve for pH, and therefore pH is equal to negative log of this value that we just solved for, and that is equal to 1.1, negative log is 1.1 e to the negative 6, 5.96. Again, slightly acidic, right? What we expect, slightly acidic. When these numbers come out, when you're doing these, you should usually be able to tell from the Ka and from the scenario if one of your numbers is wrong, because this should come out slightly acidic. So we're roughly dealing with 6 at equivalence. And there we have done calculation at equivalence. look at the stoichiometry, determine what's left over. Now we know it's acidic solution. We cannot use Henderson-Hasselbalch at equivalence. We must use the ice table. We can plug that in, Ka, sulfur, hydronium, and then sulfur pH again. Now, last step is going to be beyond equivalence. And beyond equivalence, we're dealing with 100 mils of our base and 200 milliliters of our titrant. And now that means we're dealing with 0.01 moles, 0.02 moles, minus 0.01, which is 0, minus 0.01, which is 0.01, 0 plus 0.01, and 0.01. So now, again, another scenario where we have conjugate acid left over, but we also have an excess of a strong acid, and because this is in fact a strong acid, it will dictate pH, so this is negligible. We do not concern ourselves with the value of the conjugate in this case. So the concentration of HNO3 left is equal to 0.01 moles divided by a total volume 0.3 liters, which is equal to 0.033 molar, which means that pH is equal to the concentration of negative log of HNO3, which is equal to negative log of 0.033 molar and negative log 0.033. pH is equal to 1.48, which is what we expect. Extremely acidic once this solution is beyond equivalence, and so we got about 1.5, which is roughly about there. So now we have 3 points on our titration curve. We have the halfway point of equivalence. We also have at equivalence and beyond. So what does this curve look like? Remember, this curve is not going to be sharp until after equivalence, right? We should see a sharpness after equivalence point, but it is going to be the buffering region. Remember, this is now the buffering region for this kind of titration. And this is an example again of a weak base titrated with a strong acid using the buffering region. Once you understand the basics of all these calculations, you can then use a titration curve to solve for any different aspect that you need. You can find the Ka knowing the concentrations and knowing the pH, or you can find the pH knowing the Ka, which is what we have been doing. Okay, so again, if you have any questions, concerns, be sure to email me, send me a message, or leave a message on the video, and also be on the lookout for some Workout Wednesday videos, a little more in depth on titration calculations.